So last time, remember, we Fourier transformed this one of our Coulomb potential between electrons. And we play some trick by introducing conversion factor delta, which approaches 0, but remains finite when we Fourier transform this Coulomb potential. And we show that this is given by 4 pi e squared divided by q squared plus a very small delta square. So in the limit of the delta goes 0, this so-called long-range Coulomb potential diverges in the limit of q goes 0. Okay, because there's a 1 over q squared in the denominator, and remember q represents the momentum transfer between incoming and outgoing electron states. Remember that. So in the q goes 0 limit stands for the average potential energy between two electrons. And so we need to account the number of pairs of electrons in their system, and this number of pairs approaches infinity, okay, in the thermodynamic limit, and therefore if you calculate this electron-electron Coulomb potential q equals 0 limit, you get infinity. But there's a charge neutrality condition of solids that if you sum over all the positive and negative charges, you get 0. Okay, and this is just part of the story that if you include this electron-ion attraction of a Coulomb, also in the q goes 0 limit, and also the ion repulsive potential in the q goes 0, if you add them up, and by charge neutrality condition, you must find that this should vanish. At the end of the day, so this is given by the total charge of your system, right? So equivalently. So in the same way that you can count the number of pairs of electron-ion and also the ion-ion, but when you count all the number of pairs of those charged particles and you sum them up, and equivalently you are counting the number of charges. Since net charge is 0 because of charge neutrality, you always get 0. Okay, so you don't need to worry about this infinity anymore. And so we will run into such a divergence factor before we screen the Coulomb potential. So, but later we will Coulomb screen this potential, and then we will find that this instead of a small artificial parameter delta, we get a physical quantity called Thomas Fermi screening wave vector. Okay, k squared appearing in the denominator additional to the q squared. Okay, so we will derive such a Thomas Fermi screening potential, which means that the Coulomb interaction is not long range anymore. In the realistic system, the Coulomb potential, of course, decays as 1 over r, but in the realistic case, that this is no longer a long tail that extends to infinity of r. Instead, it is along the way there's 1 over r decay, we have exponential factor which cut off the Coulomb potential between two charged particles. Okay, so that's is called Coulomb screening, and we will describe such a screening effect. So the physics is really simple behind the screening. So let me just sketch the physical picture of such a screening effect. So remember, we are dealing with millions of charged particles and also the ions. And the ions are sitting periodically on the lattice and surrounded by all this electron charge, right? Okay. So if this system consists of just two charged particles, then there's no doubt that the Coulomb potential between any single pair of electrons satisfy this 1 over r potential. That's for sure. Okay. However, there are many charged particles sitting or running in between these two charged particles, say 2 electrons, and there are negative charge of electrons and also positive charge ions. So if you look at this system far away from the from these two electrons, you'll see that this, there's something in between these two electrons which, sort of block the long-range Coulomb potential, right? So why? Because you can see that there are many interactions between different charged particles. For example, this repulsive interaction between this electron here and this red electron over there, and here and there and here and there and here and there and everywhere. So imagine that there are so many electron pairs in between any two electrons, right? So you need to take care of all these Coulomb interactions in between any pair of electrons. And that effectively screen these long-range Coulomb interactions, and so that you get some decay factor, so that when R goes to infinity, this kind of many repulsive or attractive Coulomb potentials got canceled out. So if you consider infinite number of charged particles sitting in between any pair of electrons, and there are many cancellations of repulsive and attractive Coulomb interactions. So at the end of the day, so if you look at just far away, and consider the cancellations of those repulsive and attractive Coulomb interactions, and you will find that if the distance between any two pair of electrons is long enough, which is this, if this distance r is greater than some critical distance, then there's no Coulomb potential filled by these two electrons anymore. Okay, so if the distance r between two electrons is greater than some critical distance, then the Coulomb potential for such pair of electrons almost vanishes, which means that this Coulomb interactions got screened by the presence of all other charged particles in between. So this is the physics behind this screening of Coulomb potentials, right? So we will study this, how this happens, both semi-classically and also quantum mechanically. But here we haven't addressed that issue yet, and therefore this Coulomb potential remains long range. So there's always a 1 over r, and assuming that we don't care about all the other charged particles, right? So this is the starting point of our very naive picture of electron gas in the presence of a Coulomb potential. It's very crude approximation, and this approximation is wrong. But we need to learn some lessons from this very naive starting point. And this naive starting point is called Hatree-Fock approximations. So this is the very first step towards calculating this effect of the kinetic energy and potential energy of a Coulomb interacting electron gas. So remember, we cannot solve this Schrödinger equations for that many electrons in the presence of Coulomb interactions. So we need to make some simplifications or assumptions, and this Hatree-Fock approximation is the first step with some simplified starting point. And the starting point is this. So we consider the Hamiltonian of the system as the following. This consists just a free electron gas with a kinetic energy, right? So h bar 2m k squared. So this is the kinetic energy for a free electron, and plus the long-range Coulomb potential between electrons. So we are not talking about ions at this point, okay? And this is the first thing. The second, we treat this Hamiltonian perturbatively, meaning we know the exact eigenstate of a free electron gas, in this H0 Hamiltonian. So we will define that in just a moment, this H0 and V in the second quantized fields. So we start from this non-eigenstate, so very simple naive free electron gas, and then we treat this Coulomb potential as a weak perturbation, and we treat V as weak perturbation. And we do perturbation theory in quantum mechanics, and we try to find the expression value of H, which is the eigen energy of the total Hamiltonian, approximately given by the kinetic energy of a free electron gas plus the expression value of the potential energy. But the Brown-Cat states that sandwich this H0 and the V are the states of the eigenstate of the free electron. Okay, so this and this state stands for phi 0, where this phi 0 states is the eigenstate of the H0. In other words, we start from the eigenstate of H0, and we assume that these Coulomb interactions are very weak, which is going to just modify the eigenstate or eigenenergy perturbatively, and we treat this V as a small perturbation, and we do perturbation theory in quantum mechanics by simply just perturbing this psi 0 by including this small perturbed term V. So later we're going to see that how this works. So let me just define my Hamiltonian. So H0 is simply just this, and V is the unscreened Coulomb potential. Remember, we have derived such a full operator form of Coulomb interactions. Okay, so K stands for the momentum, right? So remember, this is the interstate is what? K and K prime. And the final state is what? K minus Q and K prime plus Q. Right? So sigma stands for the spin. So sigma and sigma prime are independent spin indices. So there's a factor of 1/2 here, which cancel this 4 pi e squared. So this is the 2 pi e squared. Of course, it's a delta square in the denominator, but we don't care since this delta is 0 eventually. Okay, so this is my starting Hamiltonian, and we assume that the ground state of the H0 is the leading order state, and the effect of the V only slightly change the eigenstates and eigenenergy. So we simply treat this like this perturbatively. So that's what we are going to do. Okay, and this is so-called the Hatree-Fock approximation. So you will see in just a moment that this expression value of the V sandwiched by this phi naught state, which is the eigenstate of the H0 Hamiltonian, has two terms. One is called the Hartree term, the other is called Fock term, the exchange term. So this is the first non-trivial calculations in the second quantized form of a Coulomb interacting electron gas. So remember that this Hartree-Fock theory breaks down. It fails in all aspects, meaning we will make some predictions based on the Hatree-Fock approximation, and we can compute thermodynamic quantities of Coulomb interacting electron gas, and we can compare these predictions with the experimental observations, and we'll see that these predictions from the Hatree-Fock theory fail to explain everything that we know from the ordinary metals. Okay, so this is a very the perfect example of the failure of a very naive many-body theory, but we should learn a lesson from this failure, okay? Because the correct theory, or more reasonable starting point that departs from the Hartree-Fock theory, is precisely based on the failure of the Hartree-Fock. So if we don't, if we don't fail, and we cannot succeed. This is a very important lesson in physics and also in every subject. If you don't fail, you cannot succeed. Okay, so you can think about this sentence deeply, and this kind of idioms actually applies to every aspect of your life. If you don't fail, you cannot succeed. Success comes from precisely the millions and millions times of failure. Okay, so don't be afraid of making mistakes or failure. Okay, because the success is precisely built on the basis of a failure. Okay, you need a perfect failure at least once in your lifetime, so that you could actually learn a lesson and overcome this failure, and one day you can succeed. And that's the reason we introduced the Hartree-Fock, this perfect fail theory here to all of you, because we learned a very good lesson. And so we cannot skip this Hartree-Fock if we discuss this solid state physics. And this is a starting point that everyone can think and can actually imagine, because what we can do here. So we know perfectly this eigenstate at G0. What is the effect of the V? Well, it's just nothing but a small perturbation, and we do perturbation. We know quantum mechanics, we know perturbation theory. Let's do it. As simple as that. More complicated eigenstate of an unknown solution of a Hamiltonian may come from the known eigenstates just by perturbation. It's very naive and straightforward logic, and we'll see how it fails. Okay, so let's take a short break. When we come back, we will start to compute the kinetic energy and potential energy of a Hartree-Fock Hamiltonian. So you not only learn some physics, but you will also learn some lessons, no matter what subjects that you are going to do in your life. You may be an engineer in TSMC, the only company in Taiwan. Everyone eventually graduates from NTU, NTHU, NYCU, whatever university in Taiwan. Eventually, you will be engineer in TSMC. So that's everybody's dream. I hope not. But if you do dreaming about becoming an engineer in such a company, and you must learn a very good lessons how to actually reach the success from the failure. So this is a very interesting story, even from the point of view of the history of a solid-state physics. And this is how the theory of a solid-state physics becomes interesting. It's the first try in the theoretical aspect by Hartree and Fock, these two gentlemen, and then unfortunately they failed. But many smart guys, physicists, try to improve this by considering higher order perturbations, but it doesn't help until a very different point of view emerges, meaning we should consider not the perturbative treatment of the Coulomb potential. Remember, this Coulomb potential is not just a small or weak perturbation. So the on-screen Coulomb interactions is a very strong interaction. So on the contrary of our naive thinking that this Coulomb potential may be just a very weak small perturbation, but in fact, unless we screen the Coulomb potential, the on-screen Coulomb potential, as we just noticed that this is proportional to 1 over q squared, and when actually q is very, very small, and this term diverges, almost diverges, right? So in the q equals 0 limit, we don't care about this divergence because of charge neutrality. But even if q is non-zero but stays small, this 1 over q squared potential is really, really strong. It's going to kill your whatever ground state from the start. to significantly modify your starting eigenstate. So it is a very strong perturbation. It's not a weak perturbation. So the standard perturbation theory in quantum mechanics fails precisely because the Coulomb potential, the on-screen version, is not a weak perturbation but a very strong interaction. So however, we know that this in solid state, this Coulomb realistic solid state material, the Coulomb potential does screen, is indeed screen. In other words, in the realistic materials, the Coulomb potential will not give you any divergence of your observables because precisely the screening effect. But the Hartree-Fock theory cannot give rise to such a screening of a Coulomb potential, and that's why this Coulomb interaction stays strong all the way. And that's the key why this Hartree-Fock theory fails. But if we pretend that we don't understand this weak and strong perturbation in quantum mechanics, we just do this weak coupling perturbation theory, and then we see how this theory will lead. So we review this somewhere electron gas at 0th order. We know that this is given by what? The average kinetic energy is given by this product of these two terms that we already learned many times. Epsilon k is the average kinetic energy per electron, and this n of k is a number operator which gives you the average occupation of an electron staying in that momentum state k. Of course, you need sum over spin. Okay, so we already calculate these things, but we haven't sum over all the kinetic energy of a thermal electron gas. So let's do it. So this is the many-body ground state made of this thermal electron gas, and this is given by the product of all the single particle correlation operator. Remember that this is given by K1, dagger, K2, dagger, Kn, acting on empty state. This phi 0 is the many-body ground state of H0, okay, which satisfies this eigenvalue equation, and this epsilon 0 is the total kinetic energy of such a thermal electron gas. So let's just do it. So it's a simple algebra. Epsilon 0 is given by sum over all electrons, and for each electron you have this kinetic energy. At 0 temperature, the occupation number for electrons is occupied state is 1, right? Remember that, Fermi-Dirac. So at t equals 0, the ground state kinetic energy of such a free electron gas is given by epsilon 0, which is the sum over all kinetic energy of each individual electron states, right? So what you already learned in solid state 1. So the answer is 2.21 Rs squared Rydberg constant per particle. So this is homework, but I will give you some hints from such a calculation. This calculation goes like this. You have a three-dimensional Fermi sphere, and then you would like to know the number of states, which is the acceleration value of this number operator n sandwiched by this Fermi surface state, which is phi 0 state. And you simply just plug in this number operator at 0 temperature, which is just a theta function, and you could very easily perform three-dimensional integral over momentum variables and the polar angle and this angle phi, which is this value here. And therefore, you could figure out the relation between the number density of your electron, free electrons, and the value of Fermi momentum, where the small n refers to the number density, which is the number of particles per unit volume. Okay, so capital N divided by the volume is given by little n, and this integral that gives you the number of electron states divided by the volume is given by this equation here. So this is proportional to the volume of this Fermi sphere. Remember that is the three-dimensional integral, the k vector, and the theta function. So remember that zero temperatures only electron states that within the Fermi radius actually is fully occupied, and outside this Fermi sphere there's no electron populates there. Okay, so, and this is by orthogonal and normalization condition, this Fs and the Fs Dirac-Brown-Cass state, when you take this in the product, you get 1. So therefore, you get this relation. Okay, so the epsilon 0 is nothing but sum over this occupation of a zero temperature electron states, and you fill the gap in between. So I'm just giving you the final answer, which is kf epsilon f, or the epsilon f 2m h bar square kf squared. And then we could simply just divide this epsilon 0 by a number of particles. But if you divide the total kinetic energy by the number of electrons states, and you get epsilon 0, which is the kinetic energy per particle. Okay. Okay. So, and well, you'll find that this value is what, which is 3 pi square, 3/2 power, and n to the power of 3/2. Okay, and then you could try to use standard units such as ball radius or a Rydberg constant. Convert this epsilon 0 in units of the Rydberg constant per particle. And so let me just give you some hint. You'll need this stuff, A0, 3 nanometer, and 1 Rydberg constant, 13.6 electron volts over 2A0. Okay, so that should be enough for you to convert everything and give you this RS. What is RS? RS, R divided by A0, right? And what is R? If this is the radius of your electron gas, then this is R, which is RS times A0. And your volume, V, is the volume of this stuff in three-dimensional space. So this is just an exercise that you simply sum over this kinetic energy for electron, and from zero energy or zero momentum up to the Fermi energy or Fermi momentum. So that's all. So this is epsilon f. I'm sure that all of you have encountered such a summation before. This is just a review. Okay. Good. And this is the eigenenergy of a thermal ferroelectron gas. And you can find this formula and expressions everywhere. Ashkurov-Mermian and Kittel and Flansburg, you name it. It appears everywhere. So you can find this expression very easily, and you only need to just repeat this calculation that you have done. Okay, so so the next job will not be that straightforward, because the next thing we're going to calculate is the average or expectation value of a potential energy, and you sandwich by this phi 0, which is the unperturbed eigenstates of your thermal ferroelectron gas. Okay, so next time we will start doing this calculation, and this will be the first non-trivial task ever that you use the second quantized representation to calculate anything. And this will be the first objects that you will learn how to use the second quantized representation to to calculate the expression value of a quantum mechanical operator. And this is the first example, which is the Coulomb potential operator. Okay, so remember this Coulomb potential in the operator form contains 4 operators, right? 2 C daggers and 2 C's with different momentum and spin indices. And now we're going to contract this 4 operator stuff by sandwiching this by this phi 0. Remember, this phi 0 is a product of a single electron creation operator. Okay, and then we will see that how we could simplify this calculation. So next time, when we evaluate this potential energy from the Hatree-Fock approximation, we'll find that this will lead to a divergence of this Coulomb potential energy when we do such perturbative calculations. And that's all the troubles come from. As I mentioned, this Coulomb potential in the Hatree-Fock formulation is an unscrewing Coulomb potential, and therefore it is a very strong Coulomb energy, which is singular or divergent if we naively treat this as a small perturbation, because it's not small at all. Okay, and next when we know why this fails, then we will correct this mistaken path, and the correct approach will not be simply treating this V as a small perturbation, but we should find out what the real small perturbation is. Since the potential energy may not be that small, but there is absolutely something that's small, and that's something that's really small. We will see that this corresponds to the small density variations, meaning there's a small variations of the charge distributions in the solids relative to the uniform charge background. And that small charge perturbation is our small perturbation. But it is not shown, or it's not correctly presented in the Hatree-Fock theory. So we will address that issue next time. So now let's stop for today.